All right, this is video number 2 in this exciting series of productions on reviewing of what we've learned in Principles of Physics. So today we're going to talk about forces. A lot of things that we can talk about. First thing, Newton's laws. He had 3 of them. 1, 2, 3. The first one is known as the law of inertia. Inertia is measured by mass in kilograms in our class. So the more mass you have, the more inertia. And that is resistance to change in motion. So obviously a lineman has more inertia than a running back in football, right? They're much more difficult to move. It also means once they get going, they're more difficult to stop. So that change in motion doesn't just have to be, from rest. It could be already in motion. And the way we say that is, and you've probably learned it in elementary or middle school, an object in motion stays in motion, or an object at rest stays at rest unless acted upon by an outside force. So that's the concept of inertia. Again, it's measured strictly by mass. The second, I'm going to skip the second one. We'll do the third one next. The third one is for every action. And we can do a ... because everybody's heard that. For every action, there's an equal and opposite reaction. Basically, this means that forces come in pairs. So the force of, let's say, one object on another object, force 1 on force 2, is the same as the force that 2 exerts on 1. That's the third law. And the second law is simply an equation. It basically relates the force needed to provide a certain motion, and specifically an acceleration. This one we use the most. Oftentimes the acceleration is solved for, and it's the net force on it divided by the mass. Now the net force seems simple enough, but this is where free body diagrams come in. And again, I'm going to try and keep these videos under 10 minutes, and I think I'll have no problem with this one. So free body diagram, basically you represent, an object as a dot, and then you draw all the forces on it. So let's say you have some applied force to the right, maybe you have friction to the left, you have weight, which is force due to gravity acting downward. The way we calculate this is just the mass times gravity, and remember gravity is 9.8 meters per second squared. That'll give us an answer in newtons, by the way, for force. All of our forces are going to be in newtons. If this is something that's on a surface, the surface will push back perpendicularly, and we call this the normal force. I'll write it out, but we usually just leave it as F sub n. So what you would do, going back to, what is the whole F net, you have to look at all of these and determine what's the winning force. And the way you do that is you add or subtract. If they're in the same direction, you add the vectors. If they're in opposite direction, like these two, you would subtract them. So F net in this case would be F applied minus the force of friction. And for a given mass, that would cause an acceleration, and that would be your Newton's second law equation. Now, you might be asking, well, what about these two forces? They usually are going to balance each other out. I'm sitting in a chair doing this right now. My weight's acting downward. The chair is pushing back on me upward, and I'm not accelerating anywhere because these cancel out. Okay? So that explains Newton's 3 laws. Inertia is a big idea concept. Weight is a big idea concept. This net force and using free body diagrams to calculate it, and calculate it's a strong word because really it's just adding or subtracting. That's a big idea. If A is equal to 0, that is another big idea. Let me do a new page here. Erase all strokes. If A is equal to 0, that means when you do the math, F net is equal to 0, and that's a condition known as equilibrium. And we can have static equilibrium, or we can have dynamic equilibrium. Static, not only is A 0, but V is 0. This means we're not moving. This is kind of important for things like bridges, buildings, teachers sitting in chairs and wanting to remain in their chairs. Dynamic equilibrium, A is 0, but there's another way that you cannot be accelerating, and that's if V is a constant. And this is a good example of this would be terminal velocity, which is when you're falling or something's falling and your weight is balanced by the force of drag or air resistance to the point where these two forces cancel and you don't just stop in midair, right? You fall at whatever your V is when those two forces are balanced. So you're sort of accelerating as you go downward, but as you go faster and faster, drag gets bigger and bigger, and eventually it catches up to what the value of your weight is. And at that point right there, you don't just stop, you fall, at the same speed the entire time. And that's what terminal velocity is. One other big idea that I wanted to show you, it has to do with forces that are not aligned. So you have this and this, it's a subtraction. You have this and this, it's an addition. But if you have this and this for forces, what do? You basically move them so they're tip to tail. So here's F1. This is the tip of F1. I take the tail of F2 and put it on the tip of F1. And then the sum of those two is this. This is F, we'll call it the resultant. Okay, and if this is a right angle, which it will be in our class, you do A squared plus B squared equals C squared. So the resultant is basically the square root of F1 squared plus F2 squared. We could put X and Y for those if you wanted to. Okay, so that's pretty much everything I have in terms of forces. Let me just quick check my notes and see if I left anything out. No, I think that's good for now. Oh, one last thing. If you want to know what G is, say on another planet, you would do Fg divided by m. So let's say you go to the moon and you weigh, 300 newtons. But on Earth, your mass is 100 kilograms. We'll make the math easy. That means G must be 3 meters per second squared on the moon versus 9.8 meters per second squared on Earth. So on Earth, you wouldn't weigh 300 newtons, you'd weigh 980 newtons. So that's just a way to find what G is on another planet or a moon or something like that. All right, I'm going to stop so I stay under my